The video you're about to watch is about dual crystal transducers. It actually started out as two different videos. I bought a new UT instrument. My kids said, hey, we should do an unboxing video. And that's just dorky enough that it might be kind of fun. But the problem with unboxing videos, you have to do them right from beginning to end. And that didn't happen. So what I did was I took the beginning of the unboxing video, which has my kid's voice in it, and it was kind of fun. And then we put the dual crystal transducer video at the end. So if you can handle about 30 seconds worth of goofiness, and we get to the good stuff later.
Welcome back to my channel. Make sure to like and subscribe. So today we're going to be unboxing the Sonotest Wave. Who's preferred?
Okay, we'll do it again. Dual crystal transducer, twin crystal, dually, they're all the same thing. Maybe during your UT1 course, your teacher showed you a transducer cut in half with a transmit side and a receive side, slightly angled with the sound beam coming down, going back up again at a little bit of a V. Dualies have sort of a characteristic signal quality to them, and in order to explain what that is, first thing we're going to do is look at a single crystal. Here we have an Olympus A109S. This is a 5 meg half-inch transducer, and I'm going to put that down on the half-inch end of a steel step wedge. First thing we notice is that the first backwall echo is nice and straight up and down. Same with the second and the third, and there's very little noise or anything to speak of in between those echoes. And of course, with single crystal transducers, we do have the initial bang at the beginning, and that is because we are listening with the same element that we're using to transmit with. Essentially, with single crystals, we can hear ourselves talking. Now we'll move over to a dual crystal. This is an Olympus D790. It's quite common. It's 5 megahertz, about 0.3 inches in diameter. We'll put it back on the same end of the step wedge. First thing we notice is that there's no initial bang signal, and that's because we've separated the transmit and the receive sides. We can no longer hear ourselves talk directly, but we can hear the echo. There are, let's see, 1, 2, 3 backwall echoes in there. They are all right. The first two are good. The third one is sort of competing with a big echo in front of it. And you can see there are other little conflicting echoes popping up here and there. Those are actually mode-converted shear waves. And in order to explain why those are there, let's move over to ES Beam Tool. On ES Beam Tool, I've made a simulation of a dually probe. On the left-hand side, you'll see there's a blue transmit crystal, and on the right, there's a red receive crystal. I can use a little crop time slider here to show the beam propagation, and we can see what happens after it leaves the probe. Right away, as it strikes the entry surface, it splits. And of course, we know in UT, when a beam strikes a different medium at an angle, it will refract. And this, of course, is the principle behind shear wave weld inspection. And when that transmit crystal is angled slightly, so when that beam first comes in and leaves the end of the probe, it goes into the steel, it bends a little bit, and right behind it, it will generate a slower shear wave. Now, these crystals are not angled very much in dual crystal transducers, so we'll get a little bit of shear wave at the beginning, but not much. Now, as we continue the path of the compression wave, it goes down here, makes a bounce off the bottom, and this is the so-called V path. This is the compression wave that we're going to use to measure, and it makes the letter V. Now again, that compression wave will reflect, but it will also mode convert into shear. And then this shear wave will chase the compression wave back to the entry surface, and this is what causes that little signal artifact after the first backwall echo. Rinse and repeat with multiple backwall echoes. This just gets worse and worse. So with the transmitted wave coming down and striking the back surface at an oblique angle, the outside of the beam strikes first, and then the middle, and then the inside, and then rolls and comes up. That, coupled with the fact that we have these mode-converted shear waves, gives dual crystal transducers a sort of round mound of sound characteristic appearance to the waveform. Different dual crystal transducers have different roof angles. A D790, you can get multiple backwall echoes on them. They are okay. Some of the smaller transducers will get more and more pronounced rounding off of the waveforms, which makes it really difficult actually to use dual crystal transducers in many cases to do things like echo to echo. If you're doing thickness gauging, maybe you're using a thickness gauge instead of a flaw detector. In that case, you can get yourself a nice probe like this. This is an Olympus D7906. This is a through-coat transducer. It's a dual, but it will actually take out the paint, show you the paint thickness on the screen, show you the metal thickness on the screen without doing an echo to echo. And because it's a thickness gauge probe and it's got this fancy little pin here, when you plug this in the top, it recognizes the probe, it knows the V-path error, and it will correct itself. So dual crystal transducers, handy to have around, maybe not so great for echo to echo. Just keep an eye on the waveform. Don't just read the number off the right-hand side of the screen. Keep an eye on the waveform. Make sure the little mode converted shear waves aren't getting in the way. I hope you found this video useful. Thanks for watching.